Hello and welcome to Lecture 37 of the course From Data to Decisions. I'm Chris Mack, your instructor. In this lecture, as well as the next couple, we'll be on the topic of the independence of residuals. Going back to our list of 6 major assumptions in an ordinary least squares regression, number 3 on this particular list is that all of the residuals are independent of each other. We've assumed what we call IID residuals, independent and identically distributed. We've looked at the identical distribution idea in the past, in particular when we're talking about homoscedasticity versus heteroscedasticity. Now we're going to talk about independence. Are the residuals independent of each other? Well, the short answer is no, they aren't, and they never are. Residuals, as we know, are the variation in the data that remain unexplained by the model. So our process modeling takes all the variation in Y and says part of that variation can be explained by various X variables, the regressor variables, the predictor variables, that affect the response according to some model. And then we have some leftover random piece that's unexplained. But the assumption that these residuals are independent of each other can never be true in a regression of a finite sample. The reason is we get the residuals by subtracting from the data our fitted model. That fitted model has parameters that were generated from that exact same data set. So we have less degrees of freedom than we have residuals. The residuals are constrained in order to produce the minimum square of the residuals, the minimum sum of the squares of the residuals. If we have p fitting parameters and n data points, then we're only going to have n minus p degrees of freedom. So there is some level of interdependence the residuals have with each other because of these p constraints. Now that said, for n sufficiently large compared to p, we can kind of ignore this dependence. So if n's 100 and I have p is 3, well then the difference is not that big. And we can go ahead and assume that our residuals, or at least test the idea that our residuals are independent of each other. Just because the residuals of a fit for a given sample are not independent of each other because of this constraint with the p fitting parameters, doesn't mean we can't try to test the assumption that the residuals for the population, for the true model, if I knew the true model somehow and I calculated the true residuals, then those true residuals could very well be all independent of each other, even though model residuals for my fit are not, because of these p constraints. We're going to assume that n is sufficiently large, so we're going to ignore this effect, and instead we'll look for other sources of non-dependence, that is correlation, non-independence. Look for dependence of one residual on another. And we do that by looking at residuals in some kind of a sequence. We find that there are a number of factors that can prevent the residuals from being independent of each other. Some of them are artificial, things that we do wrong in the regression, such as model error. We're going to talk about and give an example of how model error looks like dependence of residuals on each other. But sometimes there's other things going on that we don't want, but is actually a part of our experiment. Sometimes these result in a time dependence. An example is sample aging. So I have a sample and I'm measuring it. Maybe I'm changing the temperature and measuring it again. I'm changing the temperature, measuring it again. But over time, the sample is aging. It's changing chemically. It's changing physically. It's oxidizing. Lots of things can happen. It can wear away or become rougher or whatever it might be, right? The sample can age, and as a result, we get this systematic change in the behavior of that sample over time. Or I'm making a measurement and it's the measurement tool itself that's changing over time. We have this measurement drift phenomenon where every time I make a measurement, it gets slightly bigger or slightly smaller. This time dependence can show up in the residuals and ruin the assumption that the residuals are in fact independent of each other. Another problem can be spatial dependence. Where was the measurement taken? Sometimes I've got a sample that I make measurements at different points. Maybe I'm testing soil in a field and I can't test this. I'm testing various levels of fertilizer or chemical treatments or something like that. Or maybe I'm just planting different kinds of seed along the field and then testing how fast they mature. I am forced to vary the planting of these seeds spatially in the field because I can't plant them all in the exact same spot. But maybe there's some other spatial dependence going on that isn't intended, not part of my purposeful variation in a regressor variable. This added spatial dependence can be involved with the intentional dependence, just like a time dependence can be, causing the residuals to be correlated with each other. In one sense, all of these are examples of a missing predictor variable. Time might actually need to be a predictor variable, or spatial position might need to be a predictor variable, even though I don't want it to be. I'm trying to design experiments where these aren't true. We can reveal some of these hidden dependencies, like a time or a spatial dependence, by a run sequence plot. Run sequence plot shows the residuals in time sequence, or in whatever natural order that you're trying to detect a potential systematic variation. So if we can see the systematic variation by ordering up the residuals in time, then we might be able to detect it. Here's a very important point, and we're going to see this in an example. If your time order corresponds to the changes that you make in your predictor variable, purposeful changes, you're trying to vary X and see how it affects Y. If your time order corresponds to the order in the predictor variables, well, any variation that might come from time, like measurement drift, aging, will be hidden. It will be involved into the functional relationship, how X affects Y, and you won't be able to see the difference. That's why we'll often use randomization in our experimental design. So if I'm going to vary the pressure from low to high in certain increments, I might decide to randomize which pressure I measure first and which one I measure second and which one I measure third, so that the time order is completely independent of the order of that predictor variable. In that way, we can separate any time dependence from, or spatial dependence from, the dependence on the predictor variables. If I don't do this randomization, it's virtually impossible to separate out these things. We'll also show that a lag plot, and I'll tell you what that is, can make this systematic variation even more visible than a run sequence plot. All right, what's a run sequence plot? Well, it's simply a plot of the residuals versus time, or run number, or if I made measurements, 1 to 100, first measurement I make, then the second measurement that I make, then the third measurement, etc. The run number. So here is data from data set 1 on the website. It's a data set we've looked at many times. It's measurements of a standard weight once a week for 2 years. And here's the residual from the mean value. What can we see from this? Well, I don't see any major trends going on here. It looks pretty random. Maybe I'm seeing a slight increase in the variance from beginning to the end. Maybe my instrument is becoming more and more unreliable and having more variance in measurements. in the second year compared to the first year. This is a different kind of heteroscedasticity, potentially, and maybe I want to test for that. So this gives me an opportunity to do a Bartlett test or other kinds of tests for homoscedasticity, where I divide it up by run number. So the first 50 runs compared to the second 50 runs of the experiment. On the right, I see another set of data where I have intensity measurements for a chaotic laser. This is a set of data that's also found in dataset 1 on the website for the class. And here, boy, you see lots of structure. This is not random data for sure. You can just put it in that run number sequence, and you see that there's a lot of correlation from one data point to the next. Here's another example. Here is an example where we have randomized trials. What does this mean? Well, here we have people coming into a doctor's office and getting their blood pressure measured. And then we look for a variation in one of the blood pressure measures, this is systolic blood pressure, as a function of age. And we see kind of a linear dependence where the older you are, higher your blood pressure. But the people walked into the office in random order. They just came in willy-nilly, and we measured them, and then over time we collected all this data and we plotted it up. What about the potential for a systematic drift in the measurement itself? The blood pressure measurement instrument might be changing over time. So we can plot the residuals versus run number. If we record not just the age and blood pressure, but we record them in order, in the sequence, and we preserve that information in our database of values, the run number, I could also plot the residuals versus run number. And what do I see here? Well, it looks like there's a little bit of a positive correlation. Maybe over time, drift, slight upward drift in the behavior. It's not really a positive correlation. It's a positive drift, is what I should have said. Now, we can all see that there's only a few data points here, right? 15 data points. So maybe it's way too small a number to get a good sense of whether this is a real effect or just randomness. But nonetheless, it illustrates the technique. Here's another way of looking at it besides a sequence. Here's our run sequence plot, residual versus run number. And maybe I can see some change in scedasticity, but probably not any change in the mean value of the residuals over time. Another more sensitive way of looking at variation is with a lag plot. A lag plot plots the residual versus previous residual, that is the residual lag 1, to ask, does the next data point depend at all on the previous data point? Are they linked in some way? So if I plotted EI versus EI minus 1, assuming that I've ordered the residuals in their time or other natural sequence, then I can look for that. I can discover relations between a residual and its preceding value. I can do a lag plot of lag 1 or a lag n. Lag n would mean I plot EI versus EI minus n. Back 1, maybe 2 or 3 or 4 n values, and I plot one versus the other. If there is no correlation, then this should look like a scatter plot. And it kind of does here. Everything's kind of just scattered about uniformly about the middle, 0, 0. Quick note, every data point, almost every data point, except for the first or last, is plotted twice in this graph. So for example, here's kind of an extreme data point, a value of about 33 or something. Well, we see that point here, 33, when it's the residual, and then the previous residual happened to be, minus 18 or something, minus 15. We also see that data point right here, because after a lag 1, at that point again against its previous value. And so, in fact, every point shows up on the graph twice. These are, in fact, the same residual plotted twice. That's just a way of looking at and interpreting the graph. Well, let's look at a more interesting case. This is a set of Michelson speed of light measurements. So Albert Michelson won the Nobel Prize in physics for mostly for his measurements of the speed of light. Here are some measurements from one of his more famous experiments, and it's recorded in sequence. So every measurement he made, he wrote it down in his notebook, and here is the actual numbers in run number order. All right, look at this. Can you see some systematic trends going on here? I don't know, maybe you can. You kind of sort of see some things going on, going up, going down. Maybe it's kind of hard to tell. But it's easier to tell with a lag plot. So here I plot the residual compared to the residual lag 1. I see a very systematic trend. There's a positive correlation between the residual and a residual lag 1. In an upcoming lecture, we'll talk about what to do with this positive correlation in our modeling later. But here I think it's kind of clear that there's some dependence. I don't see any data points up here. I don't see any data points down here. I only see them going in a positive correlation way. So if you're the one running these experiments and you plot it this way, you might try to understand where might this be coming from. Look at your design of your experiment, the way you carry it out, and see if you can find the source of this positive correlation and eliminate it. That's the first thing to do. If not, maybe we can deal with it statistically after the fact. But the first thing is detecting this correlation, and we can see it from these lag plots. Now, one of the most common ways of getting correlated residuals is through model error. Here's an example. Here I'm measuring heat capacity versus temperature. So I have some material, I measure its heat capacity, I change the temperature, and the heat capacity changes. Generally, higher temperatures, you have higher heat capacities. If I tried to model that as a linear model, well, I actually see some systematic variation in the residuals because of model error, right? Maybe if I look at it, maybe it's actually a second order would be a better model. But let's say I fit it with a first order model, a linear model. In this case, I did what most experimentalists would do. I varied temperature systematically, and the run order equals the temperature order. I did no randomization. I have an oven, I heat it up to 115 degrees, I make a measurement. Dial it up to 118 degrees, I make another measurement. I dial it up to 120, I make another measurement. Right? So I change the temperature in the exact same order as I'm changing the run order. In which case, any kind of experimental drift will be completely involved with temperature. There's no way to separate them. And sure enough, when I look at the run plot, but most particularly in the lag plot, I see strong positive correlation. There is a systematic dependence of one residual to its previous value. That systematic dependence goes away if I used a parabolic model. So here's my parabolic fit. Now the run order shows a lot more randomness, sequence plot, and the lag 1 plot also shows no positive correlation. It seems like a bunch of random numbers. If you have model error and you haven't randomized, then you will see correlated residuals. One residual correlated with previous residual due to model error. Well, one thing you can do is you can use this technique of lag plots to try to detect model error. You don't see it any other way. But the other thing is, you fix this particular problem by fixing the model, not by some of the other techniques we're going to talk about in an upcoming lecture. Well, looking for these correlations is one thing, testing for them is another. And we're going to talk about a couple of different tests in the future, but right now, let's talk about one thing called a run test. A runs test tests a sequence of residuals to ask, is the sequence random? If I have a random sequence of residuals, the mean value of the residuals is by definition 0 because we set it to 0 in our fitting process. So the mean value of the residuals will be 0, which means you expect about half of the residuals to be plus sign and half to be minus, about. But what we're going to talk about here is not the number, but the bouncing back and forth. How frequently will the number change in the sequence order between plus and minus? Well, if it's truly a random sequence, we can show that this bouncing back and forth from plus to minus will follow a binomial distribution. So we can compare a measured number of bounces to a binomial distribution and ask, are there too many or too few bounces for it to be a random sequence? So if the first half of the data is all negative and the second half of the data is all positive, well, that's a systematic variation. If every other data point bounces plus, minus, plus, minus, plus, minus, well, that's also not random. Right? That's a very systematic change. So if we define a run as any sequence that's on the same side of 0, we can count the runs and ask, do we have more or less than we expect? So we take our data and we just simply assign the sign, plus and minus. Here's a sequence, for example, right? First two residuals were plus, the third residual is negative, fourth residual is plus, etc. You'll count and you'll see that there are 12 pluses, there are 8 minuses, and there are 10 runs. A run would be these two. There's one run. This minus is a run. This plus is a run. This minus is another run. The 3 pluses make a run. The 3 minuses make a run. 2 pluses, 2 minuses, 4 pluses, and 1 minus. There are 10 runs in this sequence. Then we'll ask, that number of runs reasonable under the assumption that it's truly a random sequence of independent residuals. So we'll count the number of runs, R, and we'll compare that number of runs in the data to what we would expect to get if we had a binomial distribution, purely random. And that value is R, which is given by this formula, where n plus is the number of pluses, n minus is the number of minuses, n is the total number of data points, and R bar then is calculated based on how many pluses and minuses we observe in the data. We can also determine the variance that we would expect, again, assuming a binomial distribution of these runs, with this formula. So we simply count the number of runs, the number of pluses, and the number of minuses, calculate R bar, calculate the variance of R, and then create a statistic, Z sub R, which is the actual number of runs minus the expected number, if it were binomial, random, divided by variance. And then ask, is this statistic too big to be reasonable? We divide by the standard deviation, standard error rather, not the variance. Sorry. So this statistic is about normally distributed. We tend to only want to test for positive correlations. Not always, but almost all the time, what we observe in real life, in real data, is positive correlations. It's hard to find negative correlation. A negative correlation means it bounces too frequently from plus to minus. If one's a plus, the next one's minus, etc. That doesn't happen very often. It can, hardly ever happens. Instead, we usually have a positive correlation that too many are minuses and then they become pluses in kind of a bigger group. So we look for R where we have too few runs in the data, not too many runs in the data. And so we can simply do a test based on a normal distribution, a one-tailed test. All right. What have we learned in Lecture 37? We have more to discuss when it comes to autocorrelated residuals, but you should be able to quickly and easily answer each of these questions. If not, please go back and review the material. What can cause correlated residuals? That is, residuals that are not independent of each other. You should be able to generate and interpret a lag plot if the data sequence or order is known and captured in your data. Why is randomization of data order important in experimental design? And finally, what is a runs test and how is it performed? Next time we'll demonstrate some of these concepts in Excel and R, and then in the lecture after that we'll look at what to do about how to deal with the detection of autocorrelation. Till then.